Interlude, Process API. In this interlude, we discuss the process creation in Unix systems. Unix presents one of the most intriguing ways to create a new process with a pair of the system call, fork, and execute. The third routine, wait, can be used for a process wishing to wait for the process it had created to complete. We now present this interface in more detail with a few simple examples to motivate us, and thus our problem cross how to create and control processes. As what interface should the OS present for the process creation and control? How should these interfaces be designed to enable powerful and functionality, ease of use, the high performance? The section 5.1, the fork system core. The fork system core is used to create a new process. However, be forewarned, it's certainly the strangest routine you will ever call. Most specifically, you have a Linux program whose code looks like what you see in figure 5.1, examine the code. Or, better yet, type it in and learn it yourself. So let us understand what happened in detail 1p1.c. When you first started learning, the process prints out a hello world message included in the message in the process identifier, also as known as a PID. The process has a PID of 29146, and in Unix systems, the PID is used to name of the process if we wanted to do something with the process, such as, for example, stop it from learning. So far, so good. So now the interesting part begins. The process called the fork system core, which you always provide as a way to create a new process, the odd part. The process that created in an almost exact copy of the calling process that means to be a OS, it now looks like there are two copies of the program P1 running, and both are about to return from the fork system core. The newly created process called child, in contrast to the creating parent, doesn't start learning at main. Like you might expect, note that the hello world message only got printed out once. Rather, it just comes into life as if it had called fork itself. You might have noticed the child isn't a exact copy, specifically, although it now has its own copy of address space that is its own private memory, its own registers, its own PC, and so forth. The value it returns to the caller of fork is different. Specifically, while the parent receives the PID and newly created child, the child receives the return of code 0. The differentiated is useful because it is simple than a write code to handle the two different cases, as above. You might also have noticed the output of P1C is not deterministic when the child is created and there are two active processes in the system that can care about the parent and child, assuming we are running on the system with a single CPU for simplicity. Then either the child or the parent might learn at that point. In our example above, the parent did and thus printed out its message first. In other cases, the opposite might happen, as we show in this output trace. So the CPU scheduler, a topic we will discuss in great detail soon, determines which process runs at a given moment in time. Because the scheduler is complex, we cannot usually make a strong assumption about what it will choose to do, and hence which process will run first. The determinism, turns out, leads to some interesting problems, particularly in a multi-threaded program. Hence, we will see a lot of non-multimism when studied concurrently in the second part of the book. The section 5.2, the wait system call. So far, we haven't done much. Just created a child that prints out a message and exit. So sometimes, as it turns out, it is quite useful for a parent to wait for the child process to finish what it hasn't been doing. This task is accomplished with a wait system call or its multi-complete sibling, wait ID, wait PID. See figure 5.2 for details. By the way, that now this in this example P2.C, the parent process calls wait to delay its execution until the child finishes executing. When the child is done, wait returns to the parent. Adding a wait call to the code above makes the output deterministic. Can you see why? Go ahead, think about it. Waiting for you to think and done. Now you have done thought a bit. Here is the output. With this code, we now know that the child will always print first. Why do we do that? Well, it might simply run first, as before, and thus print before the parent. However, if parent does happen to run first, it will immediately call wait. This system call won't return until the child has run and exited. Thus, even when a parent runs first, it politely waits for the child to finish running and the waiter returns, and then the parent prints its message. So now the section 5.3, and finally the executive system call. A final and important piece of the process creation API is the execute, EXEC system call. This system call is useful when you want to run a program that is different from the calling program. For example, calling fork in P2.C is only useful if you want to keep running copies of the same program. However, often you want to run a different program. EXEC does just that. Okay, in this example, the child process calls EXEC repeat in order to run the program WC, which is word counting program. In fact, it learned WC on the source file p3.c, thus telling us how many lines, words, and bytes are found in the file. The fork, the system call, is strange. Its partner in crime, EXEC, is not so normal either. What it does, given the name of the executable, for example WC, and some argument, for example p3.c, it loads code and static data from that executable and overwrites the current code segment. And currently, static data with it and a heap and stack and other parts of the memory space in the program are reinitialized. The OS simply runs that program, passing in the argument as the argument of the process. Thus, it does not create a new process. Rather, it transforms the kernel running program, formerly P3, into a different running program, WC. After ESEC, the child, it is almost as if C3.C never ran, P3.C never ran. A success call to the ESEC never returns. The tip. What? Getting it right? Lamson Lamson stated in his well-regarded Hinge for Computer System Digital, get it right? Neither abstraction nor simplicity is just substitute for getting it right. Sometimes you just have to do right things. When you do, it's way better than the alternatives. There are lots of ways to design APIs for process creation. However, the combination of fork and EXEC are simple and immensely powerful. Here, the Unix designer simply got it right, and because Lamson so often got it right, we named the law of his honor. for section 5.4. Why? Motivating the API. Of course, one big question you might have, why would we build such an odd interface to what should be the simple act of creating a new process? Well, as it turns out, the separation of fork and exec is essentially in building a Unix shell, because it lets the shell run code after the call to fork and before the call to execute. This code can alter the environment of the about to be run program, and thus enables a variety of interesting features to be readily built. The shell is just a user program. It shows you a prompt and then waits for you to type something into it. You then type a command, that is the name of the executable program plus any argument, into it. In most cases, the shell then configures out where in the file system the executable resides, calls fork to create a new child process to run command, calls some variant of execute to run program, and wait for the command to complete by calling wait. Then the child complete. The shell returns from wait and prints out a prompt again, ready for your next command. The separation of the fork and the execute allows the shell to do a whole bunch of useful things rather than easily. So in the example above, the output of the program is redirected to the output as new file.txt. The greater than sign is how says the redirect is indicated. That way the shell accomplished this task is quite simple. When the child is created before the calling the exec, the shell, that is the code executing the child process, closes standard output and opens the new file.txt. By doing so, any output from the soon-to-be running program WC is sent to the file instead of the screen. Figure 5.4, page 48, shows a program that does exactly this. The reason the region is the redirection works is due to an assumption about how the operating system manages the file descriptor. Specifically, the Unix system started looking for free file descriptors at 0. In this case, standard output underscore file number will be the first available one and thus get assigned when open is called. Subsequent write by child process to the standard output file descriptor, for example, by routines such as printf, will then be noted transparently to newly opened file instead of the screen. Here is the output of the running p4.c program. You'll notice at least two interesting tidbits about this output. First, when p4 is run, it looks as if nothing has happened. The shell had just print the command prompt as immediately ready for your next command. However, that is not the case. Program P4 did indeed call fork to create a new child and run the WC program via the call to a exec with p. You don't see any output printed to the screen because it has been directed to the file p4.output. Second, you could see when a cat output file, all the expected output from the running WC is fine. Cool, right? Unix pipes are implemented in a simple way, but with the pipe existing core, and in the case the output of the one process is connected to an internal pipe, that is Q, and the input of the another process is connected to the same pipe. Thus, the output of the one process similarly is used as the input to the next, and the long and useful change of commands can be strung together. As a simple example, consider looking for a word in a file and attend counting how many times said word occurred with pipes and utility grep and WC. It's easy. Just type grep minus o full file under vertical bar WC minus L into the command prompt and marvel at the result. Finally, we've just sketched out the process API at a higher level. There is a lot of details about these calls out. There is a learned and digested. We will learn more. For example, about the descriptors when talk about the file system in the part of book. For now, sufficiently to say the fork and execute combination is a powerful way to create and manipulate processes. 5.5 Process control and users build fork and exec and wait. There are a lot of other interfaces interacting with the processor in Unix system. For example, the kill system call is used to send a signal to process, including the interactive to pause, die, and other useful imperatives. For convenience, in most Unix shell, certain keystroke combinations are configured to deliver a specific signal to the currently running process. For example, control C sends a SIG interrupt to process, normally terminating it, and control G sends a SIG TS stop signals, thus pausing the process and middle execution. You can resume it later with a command. For example, the FEG built-in command found in many shells. The entire signal subsystem provides a rich infrastructure to deliver external events to processes, including ways to receive and process those signals within the individual processes, and ways to send the signals individual processes as well as entire process groups. To use this form of the communication, the process should be the signal systems to call cache various signals. Doing so ensures that when the particular signal is delivered to a process, it will suspend each normal execution and run a particular piece of the code in response to the signals and read it anywhere else. To learn more about the signals, and there are many in precursors. This naturally relates this question: who can send a signal to a process and who cannot? Generally, the system we use can have multiple people using them at the same time. If one of these people can arbitrarily send such signals a gigaint to interrupt a process, likely terminating it, the usability and security of the system will be compromised as a result. Modern systems include a strong conception of the notion of user. The user, after entering a password to establish the credential, logs into access granted system resources. The user may then be launches one of the many processes and exercise control over them, pause them, kill them, and etc. Users generally can only control their own processes. It is the job of the operating system to parse out resources, such as the CPU, memory, and disk, to each user and their processes to meet over system goals. 5.6, before that, aside RTFM, read the man pages. Many times in this video, we are referring to a particular system called a library code. We will tell you or read manual pages or man page for short. Man page is the original form of the documentation that exists on the Unix system. Realize that they were created before the thing called the web existed. Spending sometimes reading a man page is a key step in the growth of the system programmer. There are tons of useful tidbits hidden in those pages. Some particularly useful pages to read are the main pages, whichever shell you are using, TC, SC, or BASH SC, and certainly for the system calls your program makes in order to see what return values and error conditions exist. The final reading the main page can save you some embarrassment when you ask colleagues about some intricacy of fork. They may simply RTFM. This is your colleague's way of gently urging you read the main page. The F in RTFM just adds a little color to the phrase. There. Section 5.6 Useful Tools. There are many command line tools that are useful as well. For example, using the PS command allows you to see which processes are running. Read the man pages for useful flags to pass to PS. The tool TOP is also unique, quite helpful as it displays the processes of the system and how much CPU and other resources they are eating up. Humorously, many times when you run it, TOP claims it is a top resource hog. Perhaps it is a bit of a egomaniac. So the command kill can be used to send arbitrary signal to the processes. Ascan is slightly more the user-friendly kernel, but sure to use carefully. If you accidentally kill your window manager, the computer you are sitting in front of manager, the computer you are sitting in front of may become quite difficult to use. Finally, there are many different kinds of CPU meters you can use to get a quick glance understanding the offload on your system. For example, we already keep manometers from the ranging mana software running on our Macintosh toolbox, so we can see how much CPU is being utilized at any moment in time. In general, the information about what is going, the better. 5.7 Summary. We have introduced some of the API dealing with the Unix process creation, fork and execute, and wait. However, we've just skimmed the interface. The more detailed lead Stevenson level, of course, particularly the chapters for process control, the process relationships, and signals. There is much to extract from the wisdom therein. While our passion for a Unix process API remains strong, we should also note that such positivity is not uniform. For example, recent papers by the systems researchers from Microsoft, Boston University, and ETH Switzerland detail some problems with the fork and advocate for other simpler process creation APIs, such as Spawn. Read it and a related work it referred to. To understand these different vantage points, while it's generally good to trust this book, remember too that the authors have opinions. Those opinions may not always be as widely shared as you might think. Aside, key processor API terms. Each process has a name. In most systems, that name is a number known as a process ID, PID. The fork system call is used in Unix systems to create a new process. The creator is called the parent. The newly created process is called the child. As sometimes occurs in real life, the child process is a nearly identical copy of the parent. The wait system call allows the parent to wait for its child to accomplish the execution. The EXIS family of system calls allows the child to break free from a similarity to each parent and execute an entire new program. A Unix shell commonly uses fork, wait, and execute to launch a user command. The separation of fork and execute enables features like input-output redirection pipes and other cool features, or without changing anything about the programs being run. Process control is available in forms of signals, which can cause the job to stop, continue, or even terminate. Which process speed can be controlled by particular person is encapsulated in the notion of a user. An operating system allows multiple users onto the system, and the insurers can only control their own processes. A super user can control all processes, and indeed to many other things. This role should be assumed infrequently and with caution for security reasons. References and the homework. Homework code. Okay, thank you.